Welcome back. We have reviewed math and game theory. Now it's time to start our main discussion. So the first model that we want to look into is the basic principal agent model. So it's a basic model, so it must be easy to understand, simple, right? Unfortunately, it's not easy to understand. So it's one of the models which are very difficult to understand, especially if you are not familiar with mathematical models. So I want to spend enough time to explain this, and probably I will repeat myself. I'm going to explain the same thing again and again to make everybody understand this model, because it's the basic model. So if you do not understand the basic model, you cannot understand the other models that we'll see later. So it's really important for you to understand this basic model, but it's not easy. So I'm going to be very slow in explaining this. Uh, yeah, so let's get started. So why do we uh, start our discussion on contract theory with this basic principal agent model? One of the reasons is be because it's the first topic that was discussed in this Nobel Prize document. So you read this Nobel Prize document, right? So it was an assignment in the first class. So I haven't checked it, but I know you have read this Nobel Prize document. So what was the first topic that this document was discussing? It was the tension between insurance and incentive. So to understand this tension or the trade-off between insurance and incentive, we need to first understand this basic principal agent model. So the basic principal agent model is about moral hazard. So is sorry, what's going on? So the basic principal agent model is a model about moral hazard. Uh, so it's a moral hazard model. It's one of the simplest moral hazard model, and uh, so I'm going to explain what moral hazard is in detail. So what is moral hazard? Moral hazard is not a some ethical problem. It's not some crisis in morality of human. It's not about some weird people, some crazy people killing each other. It's not about that. So moral hazard simply means that uh, asymmetric information regarding one's action. So it's an so moral hazard problem is an asymmetric information problem about action. So in other words, we call it put it differently. It's a hidden action problem. So there is an action of some people, and those actions are not observed by others. So there is asymmetric information problem. For example, uh, maybe this is not a good example because I know that you have read the Nobel Prize document, but let's assume I do not know that. So then I do not know whether you have read the Nobel Prize document or not. So that means there is something that you know, but I do not. And that information is so there is asymmetric information, and that information is about your action, right? So it's about your behavior, your deed, right? So whether you have read the Nobel Prize document or not. So that's the hidden action, right? So there is hidden action problem between you and me. So that's moral hazard. And then what is principal agent model? So the principal agent model is something like this. We consider a relationship between two economic agents uh, in which one agent called principal delegates a task or multiple tasks to the other, who will be called agent. So there is one agent who so okay, this term is a bit confusing. So there are two people. One is called principal, the other is called agent. So the principal is the one who delegates one's task to the agent, right? So there is so we call this relationship, so the relationship of delegation, a principal agent relationship. And here is the problem. So the principal cannot dictate every single move of the agent. Why is that? Because agent has free will, and the principal cannot observe every single move of the agent. Let me repeat. So the principal cannot observe every single move of the agent. So the monitoring by the principal is imperfect. So if the monitoring was perfect, then the principal would have very strong control over the agent. So monitoring itself is maybe it's not really important, but monitoring is important because it provides the uh, it, it provides the means of control. So without monitoring, without information, you cannot control other, right? So without monitoring, without perfect monitoring, the principal cannot control the agent's move. So that's one problem. Okay, so this sounds really bad because controlling others is really bad. But let's not think about that for a moment, uh, uh, because as you will see later, no one is forcing others to participate in this relationship. Everybody participates in this relationship voluntarily. So there is no really dictatorship, or like there is no really authoritarian power, uh, but just to so to speak, the what I want to say is the information is really important to make some other to what you want to do what you want, right? So monitoring or information is important, but as we all know, information and monitoring are imperfect. So the control over others, fortunately, control over others is imperfect. So instead of trying to control the agent perfectly, the principal offers a contract that gives enough incentive for the agent to work. So this is basically the narrative of this principal agent model. So probably you have heard of these terms, right? Moral hazard or principal agent model, and probably you have heard these terms in the context of discussing incentives. So principal is giving an agent an incentive to do whatever the principal wants to do. But here what I want to emphasize is that's just half of the story. The other half is about risk and insurance. So the first half is about the incentive, the other half is about the insurance. So we're going to talk about risk and insurance later. So a bit more about what's going on. A bit more about moral hazard. So moral hazard is a asymmetric information problem about action. So we also call it hidden action problem, right? So what is it? It is rather well known that if information is symmetric, the market mechanism can achieve a Pareto efficient outcome. In 1950s and 60s, this was a big deal, and really big guys like Kenneth Arrow, Gerald Debreu, they proved that uh, you know, even in situation where there are lots of markets, lots of goods, and information is imperfect, even in such case, market mechanism can achieve a parity efficient outcome. So market outcome is good. Market outcome is efficient. But they assume they allow information to be imperfect, but still they assume that information is symmetric, which means there's no information which you know but I do not. So if there is something you know, then I also know. And if there is something I do not know, then you also do not know. So information is symmetric in this Arrow-Dubrow model. But we want to uh, discuss something else. So because in reality information is not only imperfect but also asymmetric, meaning that there are things that only some stakeholders know while others do not. For example, a worker knows how much effort she spent, how much effort she put in some task, but the manager often does not. And also very important is that this amount of effort is not observed by others, and amount of effort is not verifiable. So we cannot prove that I worked really hard, right? So for example, I spent a really long time preparing this lecture, and it's not just time. I spend lots of time, I spend a long time, but at the same time, I put much effort. I try really my best. I really have done my best. So that's my claim, but nobody can prove it. I cannot prove it, right? I cannot prove uh, I actually have done my best. So effort is not observed by others, nor it can be proved. So yeah, so that's an example of asymmetric information about action or behavior. And also another example. Let's look at another example. A policyholder. A policyholder refers to a buyer of an insurance. So, for example, car insurance. So, if you're a driver, then you have to buy an insurance, car insurance. Without, if you do not want to buy, if you do not buy a car insurance, you cannot be an owner of a car. So, you have an insurance. A policyholder knows how he behaves, how he drives, but the insurance company often does not. So these days we have black box and probably CCTVs here and there. So even the insurance company has enough information to decide whether the policyholder was drunken or not, yeah, something like that. But still, it's really difficult to prove that a driver was driving recklessly or carefully, right? So driving carefully or recklessly is something only the driver knows, right? So it's not observable. No, maybe I look like driving really carefully, but maybe in my brain something else is going on. I maybe think about some movies or some work to do later. So the appearance is deceiving, right? So even if I look like driving carefully, I may be thinking something else. So there is asymmetric information about my behavior, driver's behavior. The last example, a politician knows how much money he took. This money means the public money. So a politician may take some public money in his pocket, or how much effort he put, but the citizens do not know how much money he took or how much effort he put in some important public projects. So there is also asymmetric information problem between politicians and citizens. So in all these examples, we can figure out, we can identify one party who does the task, performs the task, and another party who delegates the task. So for example, in the first case, the worker is the one who actually performed the task, the party who actually does the task, right? So the worker in this case can be called an agent, and the manager will be called the principal. And in the second example, the policyholder is the one who actually does something, driving, and the insurance company is, in a sense, delegating the task of driving. So in this example, the policyholder is called agent, and the insurance company will be identified as the principal. And in the last example, the politician is the principal. Sorry, politician is the agent, and the citizen is the principal. So, as we just saw, this principal agent model can be applied to many different contexts. This labor contract context, or the insurance, or the political economy context. So this this principal agent model is quite general and abstract, so it can be applied to many different situations. Sorry, I don't know what's going on. So the moral hazard. So just a bit more about asymmetric information problems. So there are two different types of asymmetric information problem. Probably there are more, but we just categorize. Usually we categorize the asymmetric information problem into two. One is asymmetric information problem about action, hidden action problem. It's called moral hazard. So someone's action that matters is not observed by the other party, and probably that action is not provable. It probably is not verifiable to other party. And the second category is adverse selection. Adverse selection is a hidden type problem. So hidden type means there is some characteristic of people, or some features of people, and that characteristics are important. So in the first example, a used car seller knows the quality of the car, but the buyer does not. So in used car market, there is asymmetric information problem about the quality of the car, and in this example, the quality of the car is the characteristic that matters, right? So there is hidden type problem. So type of the car is what is important in this context, and there is asymmetric information problem about the quality of the car. So this is a hidden type problem, or adverse selection problem. And in the second example, a consumer knows the willingness to pay for a good, how much she wants it, but the seller does not. So again, here the characteristic of the consumer is her willingness to pay for a good. So this is the characteristic of consumer, and the consumer knows how much she wants it, but the seller does not. So there is a symmetric information problem about the type of the consumer. So we're gonna discuss moral hazard first, and then later we will discuss adverse selection. Okay, the principal agent model. So the model looks like this. It can be described in just one slide. As I said, the principal agent model can be quite general and it can be applied to many different situations. But to be concrete, let's consider a negotiation over a labor contract or wage contract. So there is one guy who is trying to hire a worker and delegates a task to the worker, and the worker is applying for the job. So that's the situation. So and our strategy is to describe the situation as concrete as possible, and at the same time we want to abstract from many details which may matter in reality. So we want to simplify the situation, and at the same time we want to describe it as clearly as possible. So we want to describe how things going on, how things are unfolding over time. So this is a timeline. In the first stage, the principal makes a take it or leave it offer to the agent. So what is take it or leave it offer? Take it or leave it offer is also called ultimatum offer, which means so the principal makes an offer, and what the agent can do is either take it or leave it, either take it or just walk away, right? So there is no more negotiation. Just the principal offers some proposal, and what the agent can do is either accept it or reject it. By the way, the principal is the employer, and the agent is the potential employee, the worker. So in the second stage, the agent decides whether to accept it or not. If the agent rejects it, then the game ends there, and the agent will get reservation payoff U underbar, and the principal gets nothing. As we saw in the wage contract game in game theory review, so if the agent rejects the offer, then game ends right there. But if the agent accepts the offer, we move on to the third stage. So if the agent accepts the offer, the agent decides how much effort he would exert for the work, for the task. And then output, or the revenue, or the profit is realized, and the wage is paid according to the contract. So this is the timeline. So the principal makes a take it or leave it offer, and then agent decides whether to accept it or not, and then agent decides the effort level, and the output is realized and wage is paid. So as you can see, this is probably too simple to capture every detail of reality, but I think it captures really important features of reality, and it's simple, so it's easy to understand and easy to analyze. There is less room for dispute. Probably the possibility of confusion is minimized because this model is very simplified. And you may want to complicate the model further by adding more features. We can do that. We can think of more complicated model, but that's not what we want to do now. We want to start with very simple model, and we will try to understand this simple model first, And if you succeed to understand this simple model, then we can move on to more complicated model. That's our strategy. And as you will see, even this simple model is not so simple. Even this simple model is not very easy to understand. So, but let's try. X is a function of a and epsilon. What is x? X is output. So output is a function of a. Small a stands for the effort of the agent. So the agent puts some effort in the task, then the output is affected by that effort level. And at the same time, output is affected by random component. I will call it luck, or fortune. Maybe if you are not lucky, then output is small, even if you put lots of effort. But if you are lucky, then your output will be very high, regardless of your effort level. So output is a function of effort and luck. Okay. Next, the principal offers a wage W of x that is contingent on x. So the principal offers a wage which is contingent on x, which means if x is high, then wage is high, or x is small, wage is small. The principal offers such a wage. Let's pause for a moment and let's look at this wage function w. So what is this wage function w? It's a function of x. Okay, so then what's the meaning of this wage function? This wage function is the contract. Okay, this wage function is the contract. So what's written on the contract paper is this wage function. So writing a contract is come up with a wage function, coming up with how to compensate the agent's effort, which is contingent on the output. Okay, so this wage function is the contract, and we want to find the optimal contract in our discussion. So later we'll see how to characterize the optimal contract. What that means is we want to find the optimal wage function. Okay, so the wage function W is what we are very much interested. And the agent is with reservation payoff U underbar. I explained this U underbar in the game theory review. So this reservation payoff or reservation wage is the wage or the payoff or utility that the agent can get if the agent rejects the offer. So if the agent rejects the offer, the agent goes to the labor market and searching for a new offer or new job. And if the new negotiation is bearing a fruit, and then the agent will be paid, then this reservation wage or reservation pay of U underbar summarize all these process, and it summarize the expected payoff which is generated in the process. Okay, it contains the cost of searching for a new job, and it contains the future wage and everything. So that's all in the wage function. Sorry, the reservation payoff U underbar. Okay, and the agent puts effort A, which is an element of large A. So large A is the action set. So agent puts effort small a to produce output small x, where x is observable and verifiable. So in our discussion, we are gonna keep this assumption that output X is observable and verifiable. But I didn't say anything about A, right? I didn't say anything about the effort, whether it is observable or not, or verifiable or not, because we're gonna see both situations. We're gonna consider a situation where the effort is verifiable and the situation where effort is not verifiable, and we're gonna compare them, and that will show us the effect of asymmetric information problem. But we're gonna talk about that later. Let me finish the description of the model. So the principles payoffs looks like this. It's a free function. A free function is an increasing function, and also it's a concave function. So the argument of the free function is x minus w of x. So x minus w. What is x minus w? X is the output, or we can call it revenue. And from the principal's point of view, W is the cost. So revenue minus cost is the profit. So X minus W is the profit in our model. So the principal is an employer. So the principal's utility is a function of profit. So profit is X minus W, and principal's utility is a function of profit. So v function is an increasing function, so the first derivative is positive, it's strictly positive. So first derivative of v function is strictly positive, and the second derivative of v function is either 0 or negative. So v function is concave. And the agent's payoff looks like this. So agent's payoff is small u, which is function of w, wage, and also so small u minus c. C is function of a, effort. So w and effort, so wage and effort. And we're going to assume that u is an increasing function, and it is concave. So the first derivative of u function is positive, and the second derivative of u function is negative or 0. So u function is just like v function, it's an increasing but concave function. What about c? C is the effort cost. So c function is a function of effort, and it is increasing in effort, and the second derivative is also positive, which means the effort cost is increasing, and as you put more effort, the effort cost increases even faster, right? In other words, the marginal cost of putting one additional unit of effort is increasing. Okay, so this is the complete, probably it's not really complete, but it's the full description of the basic principal agent model, and we're gonna analyze it. But you may feel like, okay, it's really not really clear, right? So we don't know how to analyze it. Okay, probably we're gonna use game theory. We're gonna find some equilibrium of this game, but still it's not really easy to understand. You know, many things are undefined. For example, we said there is a random component epsilon, right? So output x is a function of effort and log, but we didn't say much about this log epsilon, right? So first we need to define what this epsilon is. We need to consider more details, and also we didn't talk much about the utility functions. We just said phi function is increasing and concave, but we don't know what exactly it is. So we're gonna need more assumptions, but for now I want to emphasize that this is the basic principal agent model, and we are gonna see two examples, and then later we are gonna consider a more general model, and which means I'm going to repeat analyzing this basic principle model at least 3 times. Okay. Okay. Let me explain. Let me explain the each assumption in detail. I assume that the principal makes a take it or leave it offer to the agent. What does that mean? We can think some alternatives like sequential offer bargaining. So the principal and the agent are negotiating over over the contract, or over the wage contract, and we can think of many different ways to negotiate. Maybe they hire someone who mitigates, who is working like a middleman, or maybe the wage can be determined by a labor union or trade union, uh, right? So in reality, there must be some many different ways to determine the wage. One way is like the principal offers a wage, and if the agent doesn't like the offer, the agent rejects it, and the agent makes an alternative offer, and the principal decides whether to accept the offer or not. And if the principal rejects the offer, then principal also makes an alternative offer, and then agent decides whether to accept it or not, uh, and and on and on, right? So maybe this bargaining process can be very long and very complicated, but we don't want to consider a very complicated model. We want to focus on very simple model. So we can think of sequential offer bargaining, and there are studies which adopt this alternative assumption of sequential offer bargaining, but in this class we are not going to consider it. We consider the simplest situation where the principal makes a take it or leave it offer, and the agent decides whether to take it or not. If the agent rejects the offer, the game ends right there. Okay. And the agent puts effort A to produce output X, where X is observable and verifiable. Here are some examples of action space, action set, and output set. So this action set A can be binary, so like no effort or effort, right? So the effort can be, the decision can be binary decision. So the agent decides whether to put effort or not. So it's a binary decision. Or we can think of discrete decision, discrete action set, but still it's a little bit more than this binary action set. So we can think of the second example, like the action set, the effort level is either 0 or 1 or 2. So the agent put 0 effort, or 1 unit of effort, or 2 units of effort. So interpreting it, we can say that the agent puts no effort, or little bit of effort, or lots of effort, right? Or we can think of action set which is continuous. So any number, any real number between 0 and 1. Or we can think of action set a positive real number, set of positive real number. So the agent can put thousands units of effort, or 10 units of effort or whatever. So we're gonna make these assumptions. We're gonna assume what the action space is. So we need those assumptions to be concrete. What about the output space X? Output space X can be binary. It's either success or failure. So the output is success or failure, or it can be discrete and finite. For example, the 0 means failure, 1 means not so good, 2 means it's not so bad, 3 is a great success, right? So the output of this business can be represented in this way. Or output can be a number between 0 and 1, or it can be some positive number or negative number too. And I'm going to explain what this observable and verifiable mean, but for now I'm going to what I want to say is these are not the same concepts. So observability and verifiability are not the same thing. So you can observe something, but maybe you cannot verify what you observed to someone else. So verifiability is a stronger concept than observability. To verify something, we need some hard evidence. It's not enough to observe some fact or some event. You need hard evidence to prove that that event has taken place. So verifiability is a stronger concept. And to write a contract about something, then we need to verify that fact, the event, or the effort level, or whatever, behavior, or whatever. So what we really need in discussing this contract theory is verifiability. To write something in contract, we need to be able to verify that behavior or event. Next, x is a function of a and epsilon. A is effort and epsilon is random component, and for example x may look like this. X is in example 1, x is a plus epsilon, right? So if a increases, which means if effort level increases, the worker puts more effort, then output x also increases, right? And if log random component log epsilon increases, then the output increases. So it's probably one of the simplest situations that we can imagine. In the second example, maybe the output is binary, right? So maybe output is either success or failure. And the output is success if a plus epsilon is large enough. By large enough, I mean a plus epsilon is greater than 10. And epsilon follows some normal distribution with 0 mean and variance 3. So we may need to make these assumptions too. We may need to be more precise about these epsilons and the output space or action space, etc. And I said the principal's payoff is increasing and concave, and okay, x is not profit exactly. So X is more like revenue, and W is wage. So X minus W is profit. And the agent's payoff is the utility. So the agent's utility increases in wage. So if you earn more money, you feel happier. So it's increasing, and we're gonna assume that U function is concave, and C function is the effort cost. So effort cost function is increasing. So if you put more effort, then you get more exhausted. So the higher, so that means you will have to bear a higher cost. Moreover, the marginal cost of putting more effort will be increasing. So C function is convex. So we make these assumptions about concavity, convexity for two reasons. First, because they make sense. I'm going to argue that these assumptions make sense. For example, this V function is increasing and concave. So it is increasing because if you earn more money, if the profit is higher, then the principal will be happier, right? So let's imagine you are running a business and your profit is high, then you will be happy. But the marginal utility of money is decreasing. So marginal utility of money decreasing means that this V function must be concave. And similar logic applies to this U function, small u function of the agent. So the agent's utility function, small u, is also increasing and concave because the agents will be happier if the wage is higher, but the marginal utility of wage is decreasing. So you will feel happy, but the increment of utility will be decreasing. So you will still be happier, but the change in your utility will not be very large if you are really rich enough. But the opposite is true for the cost, right? So effort cost is increasing. So if you put more effort, then the cost is higher. So that means you feel more exhausted if you work harder. But moreover, is more than that, we are going to assume that this cost function is convex. So what that means is marginal cost is increasing. So let's suppose that you have studied contract theory for 5 hours, and you're going to study game theory for 1 hour. So then the additional cost of studying game theory will be higher if you have studied contract theory already for 5 hours. What I mean is, let's compare these two situations. So in one situation, you haven't studied contract theory for 5 hours, and you're gonna just study game theory for 1 hour. In the second situation, you have studied contract theory for 5 hours, and then you are gonna study game theory for 1 hour. So this so in both situations, you study game theory for 1 hour, but the cost of putting effort in studying game theory will be higher in the first situation because you are exhausted. Your attention is your attention power is exhausted. You feel tired. So then that means your effort cost is higher. Alright, so graphically this V function or U function looks like the picture on the left. So it's increasing and concave, right? Increasing and concave. So the marginal utility is decreasing. So if you earn more money, so in this diagram, Z is like money, right? So if you earn more money, you feel happier, your utility will be higher. But at the same time, the marginal utility, the increment of your utility will be decreasing. On the right picture, the diagram on the right, I depicted the cost function. So cost function is also increasing, but it's convex. The cost is increasing, and the marginal cost of putting more effort is also increasing. So if you work hard and you try to work even more, then the additional cost of putting more effort is higher as you put more effort. Okay. So that was my explanation about this basic principal agent model, the description of basic principal model, and the explanation about the assumptions. But you may feel still you don't know what it is, right? So you may feel like you're a bit lost. So let's look at this example and try to understand what this basic principal agent model is about. So in this example, I'm going to make very simple assumptions, very simplifying assumptions. For example, the agent's reservation payoff U on the bar is 0, so the outside option value or the expected utility when you reject the offer is 0. And the effort space is discrete and finite. So it's like you either put 0 effort or 1 unit of effort or 2 units of effort. So small a effort level is either 0 or 1 or 2. And the output is binary. It's like either success or failure. It's either really good revenue, really high revenue, or really low revenue. So it's the output is binary, outcome is binary. So output is either high, in that case x is 10, or low, in that case x is 5. And the principal offers a wage w of x that is contingent on x, and the output x is 10. So recall that output is either 5 or 10, and the output is 10 with probability a over 2. Okay, so the output is 10 with probability a over 2. So if you increase your effort level, then the probability that the good outcome is realized increases, right? So if you put more effort, then it's more likely that good outcome is realized. And the payoff of the principal is just x minus w, simply the profit. So v function is a linear function or identity function, so the principal's payoff is simply x minus w. And the agent's payoff is similarly just w minus a squared. So I'm going to assume, I am assuming that this v function is linear, and this u function is also linear. Small u function is linear. Small u function is linear, but the cost function must be convex. So cost function is strictly convex. So I'm going to assume that this cost function is a quadratic function, a squared. So if you put more effort, then the marginal cost will be higher. Okay. So with these assumptions, we can actually solve the model. By solving model, we can find the equilibrium. We can derive the prediction of the model. But before we do that, I'm going to mention these things like probability notations. Suppose X, the output space X is a discrete state space or discrete event space, then this P will be the probability of X to be X star given the effort level A. For example, if effort space, action space looks like this, the action is effort is either 0 or 1 or 2, and the output space is binary, so output is either 5 or 10, then we can say that the probability that the output is 5 given effort level A is 1 minus A over 2. And the probability that output is 10 given effort level A is A over 2. So if the output space is discrete, then we can define these probability functions. Or we can think of continuous output space. So this large X is a continuous state space or event space. Then we can use this probability density function, right? So this F function, F is the probability density function of X given A. So for example, the effort is some real positive real number, and X is just any real number, it can be positive or negative. Then we can think of this like, this probability density function looks like this. What is this density function? This is the density function of a normal distribution. What is the mean of this normal distribution? The mean of this normal distribution is A. What about the variance? The variance of this normal distribution is 1. I hope you all understand what I mean by this normal distribution, etc. If you do not understand what I just said, then please go back to your statistics or probability theory notes and go over what you have learned. Okay, so probably you don't need to know what the density function of normal distribution looks like, but still you need to know the other terms like continuous state space, continuous event space, discrete state space. You need to understand what I mean by these. I'm not going to explain what this discrete state space or continuous state space are, but I'm going to assume you know what they mean. Okay. And then, okay, we set up the problem. We formalize the problem. There's a situation in reality that we want to describe formally, and using the language of game theory, we describe the model. We simplify the situation, we captured very important features of reality, and we make this model. And the next step is we solve the model, or we find the equilibrium, or we derive the prediction. So how do we do that? So as I explained in game theory view, we are going to use backward induction. So what is backward induction? It's a way to find subgame perfect Nash equilibrium or some other equilibrium which is similar to subgame perfect Nash equilibrium, and it goes like this. We start from the last stage and we find the optimal behavior of the later movers, and then we move backward to the earlier stages. So what is the last stage? The last stage is the agent's effort decision. So we are going to find the optimal effort first, given the wage function. Okay, so the wage function is already determined. So the what has happened is this. So the principal made an offer. So the principal made a wage function W, and the principal gave it to the agent, and the agent read the contract, and then the agent signed it. And now the agent needs to decide the effort level, knowing that or expecting the what the wage would be given the effort. So agent's problem looks like this. The agent maximized the utility, but it's not the utility that we just saw. We assume that agent's utility is W minus A squared. But the thing is, this W is a function of X, and X is function of epsilon, the log factor. So that means X is random, so W is random, right? So the agent's final payoff will be W minus A squared, but the agent, for now, the agent does not know exact value of W. So the agent maximizes the expected utility. So the agent maximizes the expected wage minus effort. So effort is something that the agent is deciding. So the it's not random variable, but X is random variable, and W is a function of X. So W is a random variable. So we have to form an expectation about W. And if you solve this model, we are gonna get this optimal effort level. Let's call it A star. And the principal's problem looks like this. The principal is also maximizing this profit X minus W by choosing W. So the principal is designing this contract. The principal is designing the wage scheme, but the principal is not able to reduce wage as much as he wants, because if wage is too low, then the agent will reject the offer. So the wage shouldn't be too low, and wage should give enough incentive for the agent to work. So the wage function W must be high enough to make the agent to accept the offer, and at the same time the wage function should give enough incentive for the agent to work. How do you incorporate these ideas? First, the constraint written here is so it ensures that the agent accepts the offer. So let's read this constraint. So the left hand side of the inequality is the expected utility of the agent, and the right hand side of the inequality is the reservation payoff. So expected payoff when accepting the offer must be larger than or equal to the reservation wage or reservation payoff of the agent. If this constraint is satisfied, then the agent will accept the offer. And also notice that this A effort is not just A, it's A star, right? It's the optimal effort. That means the principal is taking into account the agent's response. So by putting these constraints, by imposing these constraints, we can make sure that the agent accepts the offer and agents work at the appropriate level. So considering all these, the principal is maximizing the profit. So that's the principal's problem. And if you solve this mathematical problem, we will get the optimal W, and that will be the optimal contract, and that is the 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 uh, that is what we are interested in. Okay, so we want to know what optimal contract is, and that will be the prediction of this model. That will be an important part of an equilibrium of this model. Here's some remarks. Why do we analyze the problem in this sequence? Backward induction. The timeline is like the principal makes an offer first, and then agent decides whether to accept it or not, and then the agent puts effort. So we start from the last stage and we move backward. So that's how we find an equilibrium, something similar to sub-game perfect mesh equilibrium. And another thing I want you to think about is what if wx is just w? It's not a function of x, it's just some number. If wx is not a function, or it's a flat function, so it's just flat line, so it doesn't depend on x. No matter what happens, the wage level is fixed. So if a fixed wage is given, what happens? In this model, if fixed wage is given, then the effort will be 0. So if there is no incentive to work in this simplified model, if there is no monetary incentive to work, then the worker does not work. The agent put 0 effort on the task. So it is important to give enough incentive for the agent to work. Next question is, why doesn't P offers a contract that is contingent on A? Here we back to this idea of observability and verifiability. So let me explain these concepts. So if an action is not observable, then it is not verifiable. For example, an individual's effort level is not observable to the manager, then it is of course not observable to a judge in a court. Thus it is not legally provable. So you cannot write a contract based on the effort level of the agent. But there are cases in which an action is observable but not verifiable. Sometimes a person's misbehavior is observable to others, but there is no hard evidence to prove it in the court. So verifiability is a stronger property. It's a stronger concept, and in our discussion, verifiability is important because verifiability is almost equivalent to contractability. So you can write a contract based on effort if effort is verifiable. But if effort is not verifiable, you cannot write a contract based on action or effort. So we are interested in considering situations where action is not verifiable, which makes this consideration interesting, and it is true in many situations in reality too, right? So there is asymmetric information problem, which means some actions are not verifiable, which means that contracts are imperfect, right? So because if the contract is imperfect, then we are gonna lose some efficiency, and that's something we are gonna discuss later. But anyway, so this imperfection, or the imperfection of contract, or the asymmetric information problem, or non-verifiability of actions or efforts. These are the elements that make things interesting, and we want to understand the effects of these uh, imperfections, like asymmetric information, or the consequences of imperfect contract, and the consequences of non-verifiability. Okay, so that's what we are interested in. So to understand the effect of asymmetric information, or the non-verifiability of effort or actions, we are going to consider two games with different information structures. So in all games, in any of our discussion, we are going to assume that x is verifiable. The output x is verifiable. But we are going to consider different situations, different games with different assumptions on the verifiability of effort. In the first game, which we'll call full information benchmark, the action or effort is verifiable. Thus, it is contractable. So the outcome of this game, especially the effort level, is called the first best outcome. And this game itself is not very interesting, but and it may be unrealistic, but we are gonna need it because we need a benchmark, right? We consider this only to compare it with the following case. The following case is the moral hazard case or hidden action case. In this game, the action is not verifiable, thus it's not contractable, and the outcome of this game is called the second best outcome. And by comparing the first best outcome and the second best outcome, we can figure out what the effect of asymmetric information is, the effect of non-verifiability of action is. So the difference in the outcomes of the two games can be attributed to the asymmetric information problem. Okay, so we are going to consider typically in our discussions now and later. In our discussions, we are going to consider two games. In one game, we will assume that information is perfect, so action is verifiable, thus contractable. And in the other game, we are going to assume that action is not verifiable, thus it's not contractable, and we compare these two, the outcomes of these two. Okay. So if you solve the model, if you solve this basic principle agent model with the additional assumptions, then we are going to get this solution. How to get to this solution, how to get to this conclusion, is the topic that I want to discuss in the next class. Okay, bye.